So good morning, good afternoon, and good evening, everyone. Thank you for joining us today and welcome to the DAS RCN webinar on instrumentation. I am Casey Adderhold from Incorporated Research Institutions for Seismology. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Automatic captions are available to be turned on and off on your Zoom control panel. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a series of webinars on different topics within distributed acoustic sensing. I'm going to pass this to Dr. Yingping Li now to get us started. Yingping?
Yeah, thank you. Thank you for joining us today. So my name is Yingping Li, and I'm the co-leader of the Instrumentation Working Groups of the NSF-funded DAS Research Coordinator Network. Today, we will hear from some of the vendors participating in this group as a part of the series of the webinar showcase by the DAS vendors and the DAS service providers. This will establish a platform to bridge users and vendors, leading better communications among the DAS societies. We welcome the others to get in touch if they would like to present at one of these in the future. So our first speaker today is Agatha Podrasky from Silixa LLC. Present title is Introducing IDAS-MGs, Multi-Gauge Lens IDAS Performance. Agatha has worked with Silixa for the 4 years in project design and management across environmental and the industry sectors in North America. Based in the Silixa Montana office, her areas of focusing including shallow heat pump geothermal system monitorings, hydraulic applications, dark fiber data acquisition, and the seismic event detections. She enjoyed works with researchers at all stages of the projects, from design to the installation and the system commission, to technical support and the data QA and QC. So, Agatha, it's your hand.
Thank you so much, Dr. Li. I'm going to start sharing my screen.
Yes, thank you.
Can you see my slides?
Yes.
And
we're seeing just the PowerPoint view currently.
okay.
Of course. Oh, now we're seeing full screen. Great. Looks good.
So you are seeing full screen now.
Now we're, yeah, yep, full screen.
All right, wonderful. Thank you so much. So again, thank you, Dr. Li, Dr. Adderhold, and my thanks to the DAS RCN for this opportunity for me to represent Silixa and share about IDAS-MG as our contribution to this instrumentation showcase. I'll provide a brief overview of Silixa before really focusing in on IDAS-MG's performance and providing a brief case study example of an IDAS-MG deployment for seismic monitoring on a dark fiber network. And just before I begin, I'd like to quickly thank Silixa's technical team, especially Jack Maxwell and Tom Parker, and my colleagues in Silixa's environmental and infrastructure team, especially Athena Chalari, Thomas Coleman, Megan Everingham, and Wade Mendenhall, for their contributions to this presentation of IDAS-MG. Silixa is a leading independent global provider of distributed fiber optic sensing solutions and services for applications across the markets of natural environments, industrial digitization, energy, mining, and defense. Silixa celebrates 14 years with no lost time injury, with operations across sectors and around the world, with headquarters and manufacturing located in the United Kingdom, just outside of London, and offices in Houston, Texas, and Missoula, Montana, where I'm located and joining you from this morning. Silixa is the winner of several awards, most recently including the Queen's Award for Innovation, and Silixa is backed by 3 major investors and maintains ISO certification. Silixa is developer and manufacturer of the interrogator technologies at the core of all of our services, offering best-in-class DAS, DTS, and DSS interrogators. In addition to these core technologies, however, we are a full system provider. So we offer installation services and hardware, engineering design services, geophysical survey design, execution, and data analysis, as well as integrated monitoring platforms. So without further ado, I'll move on to Silixa's core technologies and the performance specifications of our latest instrument, the IDAS-MG. As we know, it is the backscatter of light that makes distributed sensing possible. So our DTS interrogators, Ultima and XT DTS, now in their second hardware generations, measure the backscattered Raman-Stokes and anti-Stokes light in optical fiber to determine temperature. Our dynamic strain sensors, IDAS, and the Carina sensing system determine strain rate in distance for measuring phase change in the Rayleigh scattering signal. And Silixa's Carina sensing system specifically utilizes an advanced interrogator paired with constellation fiber to gain a noise floor that is 2 orders of magnitude lower, equivalent to 100 times or 20 dB improvement over standard fiber, which is truly transformative for some key applications. Constellation fiber doesn't just enhance backscatter, it also maintains the phase coherence of the light and provides uniform noise floor performance with distance. IDAS-MG is based on Silixa's already class-leading IDAS system, but now with user-selectable gauge lengths of 3, 5, 10, or 30 meters. So these gauge lengths were chosen as an optimal selection for the best overall measurement range, spatial resolution, and noise floor flexibility. IDAS utilizes highly phase-sensitive balanced interferometric detection that is fundamentally shot noise limited. So using a balanced interferometer removes the effective phase noise as each pulse interferes with an exact delayed copy of itself. The linear amplitude and phase response of IDAS offer stable repeatability for seismic applications and no crosstalk between channels. There's real-time data visualization for all channels, and I'll share some movies of the real-time data later on in the presentation, with very good SNR and a broad frequency response. The IDAS-MG specifications shown in the table here are based on rigorous lab-based assessment of performance using CFOM recommended testing practices. So for each gauge length, the table provides the maximum sensing range, and I'll talk about how that maximum sensing range is determined and defined. The noise floor, given as the median amplitude spectral density at 1 kilohertz, and the typical 10 hertz dynamic range. The minimum sample spacing at all gauge lengths is 25 centimeters, with a maximum spacing up to 32 meters. There's a maximum limit of 40,000 samples, so for longer fiber distances, the samples must be spaced further apart, with spatial resolution being defined as 1 gauge length. IDAS is capable of sampling frequencies from 400 hertz up to 100 kilohertz, which allows acoustic sensitivity to signals from less than 1 millihertz up to 50 kilohertz. The fastest sampling frequency on a fiber is of course limited by the length of the fiber, as only 1 pulse of light should be traveling in a fiber at a time. So I'll now go into more detail on how these performance specifications were determined with the lab tests. The noise floor was determined for each gauge length setting using the CFOM recommended test setup, where the IDAS MG is connected to 5 kilometers of single mode test fiber in an acoustically isolated chamber. The ASD plotted here is the medium value of the noise along the whole fiber, which would be marginally higher at the end than at the start. So as the medium amplitude spectral density, this provides a good comparison or good representation of the noise floor. And to accurately compare system noise floors, it's important to know what value is being used as the stated noise floor, whether it's the medium amplitude spectral density or at near or far channels. So in general, the noise floor goes down as gauge length increases, and the ability to record smaller events improves with longer gauge lengths. So for example, at 30 meter gauge length, the 1 kilohertz ASD is 0.6 picostrain per square hertz. This means that if you recorded 1 second of data, you could detect a 1 kilohertz sine wave down to 0.6 picostrain per square hertz amplitude. So in 2 seconds, you could measure a signal that is quieter by a factor of √2. And with an even longer measurement, you could further improve upon that. But this noise floor tells you how quietly you could measure if you only measured for 1 second. Self noise is demonstrated on a quiet fiber section, but dynamic range is demonstrated by a loud signal. The higher the dynamic range, the more accurate the quantification over strain rate over an extreme range of amplitudes. So to test dynamic range at each gauge length, the IDAS MG was again connected to the 5 kilometer single mode test fiber, but this time the end of the fiber was connected to a fiber stretcher. So the dynamic range depends on the length of measurements. So for a 1 second FFT at 100 hertz, 30 meter gauge length, the dynamic range here is measured to 110 dB, with other values given in the table here at different gauge lengths and at different frequencies. So this means for the 30 meter gauge length at 100 hertz, the loudest measurement signal amplitude is 10 to the 5.5 times greater than the noise floor. If you measure for twice as long, the dynamic range increases by 3 dB. And the 1 second result that is quoted here from the tests on the CFOM fiber is the most stringent definition of dynamic range. So it's worth requesting this value for comparisons of dynamic range between instruments, though I hear it is much more challenging to achieve this test result. DAS sensing range is the hardest specification parameter to specify and to evaluate. It's demonstrated on standard single mode fiber with no point losses. And again, the CFOM recommended test setup was used for IDAS MG to determine the measurement range. During testing, many different fiber lengths were used to see at what distance the signal from the fiber stretcher became no longer measurable. So standard field settings were also used for the interrogator at this point, so that the test would provide a relevant definition of range. Greater range could be possible, but it would involve compromising the spatial resolution, and that wasn't really considered to be practical for defining the range of the instrument. So in the plots here, you can see the measured signal at the specified range for each gauge length. At the maximum range specified, that acoustic noise is still at least 10 dB below the maximum noise, with the range increasing as the gauge length increases. So finally, here are the test results demonstrating the signal detection frequency range. For these tests, the end of the fiber was modulated with a piezo chip at 50 kilohertz, with the IDAS MG measuring with a sampling frequency of 110 kilohertz. The low range test results plotted here were with a signal frequency of 5 millihertz with 800 hertz sampling. Frequencies less than 1 millihertz have been recorded and published by several of our clients working with IDAS. So to finish in the back half of this presentation, I'm briefly going to share a Silixa case study in progress with an IDAS MG deployed just last week on a dark fiber. So for those of you working with DAS and dark fiber, gaining access to dark fiber owned by telecom providers can be a really significant challenge to exploring the possibilities of using DAS for seismic monitoring on a dark fiber. And there often isn't a fiber length choice. You must make do with what's available from the provider without the option of terminating the fiber shorter. So depending on what's available and what data you're interested in collecting, and also what ambient signals exist in the region of interest, it can be really advantageous to have the flexibility to acquire measurements at different gauge lengths. So we're excited to have an IDAS MG to deploy on dark fiber and take measurements at these different values. So we're fortunate to collaborate with Three Rivers Communications based in Fairfield, Montana, to connect IDAS MG to a 32-kilometer long run of direct buried dark fiber for testing purposes. So just to sort of show you where we are in the world with this project, here we are in Missoula, Montana at Silixa's Environmental and Infrastructure Office. And Fairfield, Montana is about 150 miles northeast of Missoula. So it's about a 2.5-hour drive across the mountains to deploy the instrument in Fairfield. And Three Rivers Communications has hundreds of miles of dark fiber, but we've specifically connected to a 32-kilometer run shown here in the red line, running west towards Augusta, Montana. So Montana is the 4th most seismically active state in the US with 7 to 10 earthquakes a day, making this location a really good test bed for using IDAS MG for seismic studies. And typically 10-meter gauge length DAS offers the optimum combination of SNR performance and range for seismology applications. But the lower noise floor possible with a 30-meter gauge length allows for detection of lower amplitude signals. So with IDAS MG, we plan to acquire test data at both gauge lengths. The IDAS MG data acquisition provides real-time visualization of data in different modes. So shown here is a screenshot of acoustic mode while acquiring data on 32.1 kilometers with 1 kilohertz data output and 1 meter sampling interval. It's quite small to read the axes on the plots since this is a screenshot from the full resolution display, but on the top is plotted strain rate in nanostrain per second versus fiber distance. The middle plot is strain versus time, and the bottom plot is the strain power spectrum versus frequency. So the bottom 2 plots are output from one channel selected with the red cursor on the top plot, which is currently all the way at the left at 0 fiber distance, which is defined as being at the connector at the front of the IDAS. So the vibration seen in the strain versus time plot, that's the middle plot, is from the HVAC running in the room where the IDAS is deployed. So here's shown a comparison of the acoustic mode plot of strain rate versus distance when the IDAS MG is configured at the different gauge length options. So here we're users defining the gauge length and keeping the data output at 1 kilohertz and the sampling interval at 1 meter. The X and Y axis scales are the same in each plot. So moving top to bottom from 3-meter gauge length to 30-meter gauge length, you can very easily see how the amount of noise with distance diminishes as that gauge length increases. Here's another comparison of the dark fiber system noise floor at the 4 gauge lengths with a plot of the measured system noise level at all channels compared to the theoretical system noise based on the instrument settings. And the straight lines here are the theoretical, with the jagged lines being the measured noise floor from data collected at each of these gauge lengths. So in my last few minutes, here's a video of the real-time waterfall plot of the 30-meter gauge length measurement, where distance is on the y-axis, time is plotted on the x-axis, with 0 at the top being at the connector. So we're increasing distance from Fairfield toward Augusta as we move down the side of the screen. And the color scale is in RMS strain rate. And here the view started by showing the entire 32-kilometer fiber length and then zooming in on some of the signal. So this is most likely just from moving vehicles between Fairfield and Augusta, with this video taken yesterday. So moving forward with acquisition with IDAS-MG on this dark fiber network, I'm hoping to have some real-time observations on site to correlate some of the signals we're seeing with different vehicle types. There's also construction going on near Three Rivers Communications office, so we can pick out some of those signals as well. So, and here's another waterfall plot now with the 10-meter gauge length, with this starting with the same strain rate color scale as for the 30-meter data that we just showed. So you can see how the noise with fiber distance is greater than with a 30-meter gauge length. And again, we can zoom in on what is most likely vehicle traffic, possibly very fast cows. So last week we had a team on site doing tap test mapping of this fiber run. So from my office in Missoula, 150 miles away, I was able to coordinate the tap testing with our team out in Fairfield, and also let them know whenever a car was approaching along the road where they were doing their tap testing. So finally, I've yet to catch an earthquake when viewing data live. Our earthquake seismologist says I should have been recording this past weekend, however. But I really look forward to acquiring more test data from Fairfield, as well as participating in the DAS RCN Global DAS Data Campaign that's coming up in February 2023. By acquiring data continuously on the Fairfield fiber and then making that data, sharing that data with the DAS community. So just a quick note as well that if you're fortunate to have access to dark fiber, but not an interrogator, to please get in touch with us. We'd love to connect people with interrogators so that they can participate in this exciting campaign. So thank you for listening. I'll do my best to answer any questions, and several members of Silixa's technical team who conducted the lab tests are likely also on the call and may be able to help answer some questions as well. So thank you so much.
Thank you. So if you have any questions, just stand to the box. Okay, we have one question here. I think from the Roger Krakenmores. On the Silixa system, can measurements at a different gauge lengths be collected at the same time?
So no, they can't.
So we have another question here. Is Mano Bashman, the plot that creates the magnitude versus the distance on the fiber show the recorded data and the theoretical response. Maybe I'm making a mistake, but it seems the recording data are the better qualities than the theoretical response. Could you comment on that?
So that's often the case. That plot was generated using a noise check tool that calculates the theoretical response just from system settings. So the theoretical calculation of the noise floor is often different than the actual measured. So I'm not sure if anyone else from the technical team is available to more thoroughly answer that question, but it's a model versus reality.
Okay, thanks. So we have another question here is by the Jiaji He. Can you hear me? So I just get some internet signal is not good. Okay, that's just from Jia He's questions. Thank you for the wonderful questions, Jonathan. With acquiring the parameters like the measurement range recording to the C-form standards, does Silixa use the standard single mode fiber or scattering enhanced fibers?
No, all of these tests are performed on standard single mode fiber.
Okay, that's great. So any more questions from audience?
Yes, Agatha, I'll ask a question about the size of the data that are collected at different gauge lengths. Is there a savings in the amount of storage required at longer gauge lengths?
So often the longer gauge lengths are used for longer range measurements. So the longer the range, the larger the measurement anyway. But there is a savings in increasing the gauge length and the spatial sampling as well. So at long range, because of the trade-offs you need to make in the configuration to acquire data on a longer range, you decrease the data size, but you're still recording on a longer fiber. So there are trade-offs in data size.
But per kilometer, there is a savings in the amount of data collected at longer gauge lengths.
Yes, but the size of the data file also depends on the sampling frequency and the sampling interval.
Sure.
So it could be possible to measure, I'm not sure why you would do this, but to measure with a long gauge length at a high frequency and a fine spatial sampling, and then the files would end up larger.
And since it's software selectable, does that mean that the gauge lengths are done at longer gauge lengths through some kind of averaging?
No, it's not done through averaging.
Oh. Can I ask how it is done then?
Is a member of the technical team on the chat that could respond?
If you raise your hand, we can also have you unmute.
Hello, can you hear me?
Yes.
Thank you,
Hi
Jack.
there. Hi, yeah, this is Jack Maxwell from the technical team. Yes, we have a system which allows you to choose between different optical paths inside the interrogator, and the different paths allow you to move to a different gauge length. So it's not a post-processing technique, it's an optical technique which allows essentially the ultimate noise floor characteristics on each gauge length setting.
So you're actually changing the reference length of the internal fiber.
It's related to the optical paths, yes.
Thank you.
Thanks.
Okay, good. We have another question here. By the Sakio diet. The gauge length makes operation along the scattered points to give one single value per channels. What kind of operation does it do? Like average values along the scattered points inside of gauge length, or is more of the Gaussian, where in this middle of the gauge length has more weight than the edge of the gauge length?
So I'm afraid I didn't quite catch all of the question, but perhaps I can open it in the chat to view it.
Yes, if you check the Q&A, you should have access to the text there.
The gauge length makes an operation along the scattered points to give one single value per channel. What kind of operation does it do? So the gauge length is a moving window, in this case of different lengths, centered on the sampling location on the channel. So for each channel at the sampling interval, the output signal amplitude is the strain rate amplitude measured over that gauge length. So for 3 meters at 1/4 meter sampling, the output of the system is the strain rate measured over that 3 meter window centered on that location. Then if you move to the next channel, a 1/4 meter away, you're again looking at the 3 meter window of dynamic strain centered on that point. So that's why you have a limitation on the spatial resolution of the system, because while your sampling interval may be finer than the gauge length, you're still taking a measurement over a gauge length sized window centered on that point. So you see a blurring at the edges of specific signals based on that gauge length window. Does that answer the question?
Yes, I think
Okay.
it's answer yes. Okay.
Good, thank you.
Yeah, any more questions? I have questions. So if you look at the waterfall plot for the 32 kilometers, the fibers, so you can see some of the signals looks like the traffic because they have the move out at the time. But also we observe some of the noise or whatever signal or noise is really parallel to this timeline. It sounds like they're at certain positions. So as any thought on about all of this, it's kind of some localized noise along the fiber, or what else could be the possible reason for all of the signal or noise just all of parallel to your time axis?
Yeah, so this fiber is directly buried along highway and backcountry roads. So some of the stationary signal or some of the stripes you may see in the waterfall plot are due to just naturally noisier channels based on the installation of the fiber itself. So some of what you're seeing has to do with the installation, and that would need to be better correlated with the tap test. There are a number, since this is telecommunications fiber, there are a number of handhole boxes that have large coils of cable inside of them for slack loops and for extension purposes. So those are also creating some noisier seeming sources because of different coupling inside of those boxes. And then in the waterfall plot, it's important to remember that real-time data visualization doesn't have any frequency filtering. You're just looking at the raw signal amplitude at all frequencies in time. So to pick out specific signals with distance, you would really want to filter that data. That's another reason why you're not going to see an earthquake necessarily in live view, because you're just looking at raw signal amplitude rather than filtered data. So, and in the waterfall plot, all of the traffic signals that were zoomed in on there were closer to the start of the fiber. That's not because we can't see those traffic signals further along. It's because that fiber starts in the town of Fairfield, where there is more traffic, and goes out into the country where there is very little traffic. So I've spent quite a bit of time watching the waterfall plot, and you do see clear traffic signals at 32 kilometers, but there just aren't as many things moving around out there as there are in the town. So I hope that addresses some of what you're seeing on the waterfall plot.
Yeah, thanks. So I think that's very interesting because you mentioned about the participation for the the global seismic monitoring. And also, I think that's important. Right now, you can look at all of the fiber lengths and to see which part is probably most quiet and which part is noise part. So then when the really earthquake happened, so we can know which portion of the fiber is the best for the purpose of recording the earthquakes. So I think that's a good testing, and this system is available there, and looks like a majority portion of the fiber looks like quiet. So that's good. That's good signal. So we can just use that one for this earthquake seismology monitoring. Thank you.
Yeah, thank you.
So anyone more questions? So we're perfect on the timing. So the things like we don't hear the 7 speakers join us from the website, and we don't know what's the reason for that. So I think I will be hand over. So we will be close this earlier. So I will hand to the Casey. So this is will be this great presentation. Thank you for the for your wonderful presentations as one of the audience said. So it's great to introduce this technology to let the audience know. So I hand over to the Casey.
Thank you so much, Yingping. And yes, thank you to Agatha for her presentation today. Thanks to Jack and Herb and all the other participants in the session. The recording will be made available on the IRIS Earthquake Science playlist. If you're interested in future DAS webinars, please join the DAS mailing list and check out the DAS RCN website. Got some good stuff coming up. And thanks so much for joining us today.